Okay, for those of you that connected to the Zoom meeting, to virtual meeting, good morning. Today, we are going to discuss about the IEEE 100, which is basically the standard terminology in engineering. Okay, but I want you to note that today we are not just learning the definitions. Okay, we are actually learning a tool that is very critical, and without it, no system, really, no system you ever design will survive outside of your room. Okay, so this is very critical standards. Let's move on to the role of this standard, why the language in engineering matters. Okay, in engineering, the language is very critical. It's not a casual thing. Okay, the terminology is very important. Language basically is design, okay, is the contract that you make as an engineer, your responsibilities. Language is the compliances. Language is testing. Okay, if you design something and you are going to evaluate that, it is your writing, it is the language that you use that design how to test that technology. Language, this is very important. Language is safety. Without a precise writing, engineering writing, you are going to make hazards. You are going to endanger safety of the users and other engineers, okay? And the language is actually a legal accountability. So if you have a vague language and you don't follow the terminology, the standard terminology, basically you are responsible for any loss, either financial or like human lives. We are going to see some examples, some very famous examples that I think it's going to blow your mind of how the terminologies, how the standard writing could affect the result of even the most sophisticated designs. Okay, if the design that you describe is ambiguous, basically it doesn't matter how brilliant your work is, it is going to fail. It doesn't matter how elegant your coding is, if your description is vague, okay, your system is going to fail. Is not going to survive outside of your room, of your designing room. Okay? Now, let me ask you a question. How many of you have casually used the word ground in your writing? How many of you use the word ground in any of your design reports, the manual you write, probably the capstone project that you had, any kind of show of hand? Okay, now I want you to remember that. Another question. Do you think ground means has the same meaning in power system or in signal processing or in communication or medical device? No. That's what we are talking about. Simple word. This is one example. Simple word. Ground in different domain of electrical engineering has different definition. So you can't just casually use a word in your description and in your writing. In reality, like for example, we have different type of definition for ground. Like in some of the systems, we have protective earth ground. This is one of the specific definition of the word ground. Okay, what that means is that's actually a protection, a human safety protection. when you kind of like prevent any hazards for the users against electrical shock or electrical kind of like hazard. In signal processing, ground means something else. It's actually the reference signal. Okay, so that's basically is very critical to know what it means, what is the meaning of the ground is in signal processing, because that's how you define low nodes with that ground. See how difference it makes. In one domain is protection against safety hazard. In one domain is the basic of definition of the low noise. So it's basically a reference signal. Okay. Now, what is chassis ground? Maybe you heard about that. Chassis ground is basically a metallic bonding between the frames, okay, the frames of any equipment or electronic equipment to prevent electromagnetic interference. So you see in three different domains, we had three very different meaning for one word. Okay, so ambiguity could destroy basically your design, destroy your any kind of like even brilliant idea that you have. Now, there are several catastrophic incidents that happen only because the languages. That I want to like remember and like pay attention that how terminology could end in a very devastating situation. The first example that I'm going to mention is NASA Mars Climate Orbiter. In 1999, we lost a $300 million project just for terminology. There is no error in the design, only terminology. Between 2018 and 2019, the Boeing 737 MAX has several failures that not end up in $1 billion of financial costs, but more importantly, their human life savings. The reason is what? Terminology. There is no technical mistakes on those projects. It's just terminology. How important it is. We had through 2012 to 2020, we had several recalls for medical devices. You understand how effective is the medical devices are directly connected to the human safety. There were recalls for those medical devices because the malfunctioning in them, which is caused by vague and ambiguous statements, not professional or standard terminology. We are going to go deep into that to show you in each of these cases what mistakes happened based on that terminology, so you could know, okay, what is happening, and you have like a better sense of these three examples that we are going to talk about. Now, let's talk about IEEE 100. Basically, what we say so far is why, basically the reason that engineering standards exist. Because we need a standard language, okay, between all the engineers to talk to each other, to transfer ideas, okay? Now, why IEEE 100 exists, 100 exists? Because we need to start thinking, we need to start designing, and we need to start writing, okay, like a real engineer, like a professional engineer, okay? Without it, our systems, our design would not survive. That's very important. But what exactly is the IEEE 100? The IEEE 100 is not just a text, is not just a dictionary, okay? It's basically, and it's not just like a casual glossary, okay? It's basically a formal, authoritative dictionary for our profession. What that means? The official title of that IEEE 100 is the Authoritative Dictionary of IEEE Standard Terms. Okay? And it basically has a very strategic role in electrical engineering. Now, the key functions in IEEE 100, what is the key functions of that? This is important. Okay, we know what the goal is. We know what is the purpose of this. So far, we discussed that what is the purpose of this IEEE 100 is, but what function does it have inside the IEEE 100? Okay, first of all, it's create definition consistency. What that means, imagine you're designing like a power inverter, okay? And your supplier, your customer, and your regulator, okay, plus your safety agency, all have different understanding for terms like voltage or that example that we made, ground. What's going to happen? Or they have different understanding about total harmonic distortion or related load. Okay, so what's going to happen? Basically, your system would fail because different teams that have to get together to basically transfer that design from the pure idea to a commercialized device. They have different understanding, meaning in each phase, those teams would do their job based on different idea and different interpretation. Okay, you probably could imagine what's going to happen after that. Okay, next one is the cross standard alignment. Each equipment that you are going to build in industry, everything that you are going to do in industry has a standard. What you learn in college or like through master degree, if you continue that, or like through the PhD, they are all fundamental basic theories. Those courses would help you, okay, to basically understand what's going on. You are not going to use exactly those concepts in an industry. In an industry, these are standards that you have to follow. Basically, I used to say like the standards are the Bibles in electrical engineering or in engineering. You wanted to go through salvation, you have to follow that. Okay, follow those standards. There is no, I don't want to, I should not to. You have to follow the standard. Now, we have different standards for different technology, for different devices, for different domains. Okay, how these are connecting to each other, how these different standards are aligning to each other using IEEE 100 by setting a precise single standard definitions. Okay, the last but basically the most important part is the legal and regulatory authority. Without the definition, the rules that you make, or any regulator that you make, or the a specification or criteria that is defined for any technology is obsolete. It doesn't mean anything if you don't follow the standard definition. Now, let's talk about how the IEEE 100 is structured. IEEE 100 is basically an organized alphabetical terminologies. Okay, it's a dictionary that is organized alphabetically. Okay, but it's not that just that. Every word is also categorized, okay, into a certain subfield of electrical engineering. Like, for example, they could be categorized in control system or power or signal processing or communication. Okay, so those alphabetically ordered terminology, okay, are also categorized and may have different meaning, different definitions in different categories. Okay, normally when you open up the IEEE 100, you see the list of words. The term itself is normally in boldface, okay, and it follows with the exact, precise, quantitative definition. Okay, some of the terminologies might have some note that helps the clarification of those definitions for the audience. Okay, but this is basically the structure of IEEE 100. Now, how you can read the IEEE 100 terms, how you can understand them. Okay, when you want to use the IEEE 100, okay, for any terminology, the first thing that you have to do is to recognize if that specific term is categorized in a certain domain, or it's a general kind of like terminology, okay? And if it's categorized, which category are you looking for? So you have to first identify the category of that terminology that you're looking for, okay? After that, you are looking in a formal construction of that definition. Now, what's that? Why is important? Because, like, for example, if you want to use the term voltage, okay, the voltage has a specific definition in that IEEE 100. That specific definition has several characteristics for that terminology. Now, every time you use the word voltage, you can't just casually drop that word into your writing. Your writing is not just voltage. You have to enter exactly those characteristics, okay, that is in the definition into your writing. We are going to see some example to see what I'm talking about, okay? What is the next part? We are always talking about that. You always heard about that. Unit and measurement. There is no parameters. There is no meaning to any parameters, okay, without the unit. If you don't mention the unit, it's worthless. If you don't mention how you could measure that quantity, how you can evaluate if you are in a normal state or you have fault or you have kind of like in a transient kind of like a state, okay, if you don't define the protocols for the measurement, the conditions for the measurement, it's worthless. Because, yeah, you define the voltage for a certain level, but if you can't measure it, what's the point? If you can control it, what's the point? Okay? And the last part is cross-validation. It's not just IEEE 100 that you have to pay attention. Any device that you are going to design or any process or any system that you are going to develop in industry, as I said, has a different standard, has its own specific standards. And it's not just one standard. Be careful, okay? Every technology, any device has different standards from different aspects of that technology, okay? Now, if you're using a certain definition for any terminology, you need to cross-validate with that standards because sometimes they need to change something. And if you don't cross-validate, again, you are using a wrong definition. Are we good? Now, how you can apply IEEE 100 in your writing. Okay, so far we see why it's important. We discussed that. We discussed what's in that IEEE document is. We discussed how to use it and what is the basically the importance of it. Now let's say what is the step-by-step process that you can apply that IEEE 100 standard in your writing, in your design. Okay, this is basically a cheat sheet. Okay, now if you wanted to like apply IEEE 100, first thing that you have to do is to look at your writing and identify all the nouns plus their adjective. Every single noun that you use in your writing plus the adjective. Now, if you find those nouns, now you have to cross-check with IEEE 100. Is there any standard definition for that term? And if it is, remember, it's domain domain of the definition is important. Okay, in which subfield of electrical engineering you're looking for the definition of that term. Okay, if there is the definition in IEEE 100, what is that, and what are the characteristics that you have to keep in mind when you talk about that parameter? Okay, now when you cross-check with the IEEE 100 definition, now you had to rewrite or modify what you wrote for that terminology. Okay, and then validate for consistency again, double check if you didn't miss anything. So this is a step by step. Identify the nouns and the adjectives. Okay, cross-check it against the IEEE 100, modify it, double check. Let's look at the term voltage. For example, the definition of the voltage in IEEE 100 is the difference in electric potential between 2 points in a system. Okay, there are several important part in that definition. You might think, okay, we already know that, but there are several important parts in that definition. What is that? First of all, it's a difference. Okay, it's not an absolute number. Voltage, or if you wanted to look at it mathematically, is a vector, is not a scalar. Okay. Second, it defines electrical potential. Okay. The casual kind of like the one of example is the casual referencing to the batteries. When you want to say, okay, well, how strong is the battery? You use like, okay, this is like a 3-volt battery or 9-volt battery. That's basically a nonsense, because that number is the potential difference between the 2 poles of that battery, not the energy, not how strong that battery is. Okay, I wanted to give you an example of what I mean based on this terminology. Now, next terminology, it always defines a difference between 2 points in one system. So you cannot simply say, okay, the voltage at point A is blah, blah. You have to define it, the voltage, the different potential, the difference of the potential between point A and point B. Now, when we casually is used in a writing that normally in a system, you say, okay, this point voltage is like 2 volt. Okay, in your writing, but that's not accurate. The professional statement is that the voltage from that node to the ground is blah blah volt. Okay, so that's kind of like so the voltage has two points. It should be defined between 2 points. If you casually mention, okay, the voltage should be 600 volt. Okay, where? Between which 2 points in your system? Is it the input terminal between the null and phase? Is it the cross of one resistance? What 2 point? Which 2 point you're talking about? Okay. Now, let's again use another example. The word ground that we used uh, uh, before as an example. As we said in signal processing, we define the ground as reference point for a signal voltage within a circuit. Now, in protective earth, we mean the connection intended to protect persons from electrical shock by bonding exposed conductive parts to the earth. These are important. When you want to like define protective earth in your design, you need to mention each of those parts that I highlighted in that definition. You can't say, okay, connect the protective device. You need to say connected the protective earth, okay, to prevent which electrical shock. What electrical shock? Is the voltage? Is the current? Okay. Bonding, what exposed conductive? Which one? Where in the system? To the earth connection. Is that clear? Okay, yeah. Or what chases ground, which is basically is the metallic frame of equipment to the ground connection, to the earth connection. Next terminology that I want to like show you how important the definitions are in electrical engineering. Rise time. Probably you use that or you read that regularly in the engineering writing. What is the definition of the rise time in IEEE 100? It is the time required for a signal, okay, to change from a specific low value to a specific high value. You can't just say, okay, the rise time is 5 nanoseconds. The rise time of which signal? How you define the rise time, that 5 nanosecond period that we are eventually wanted to like evaluate. We wanted to like measure to see if we're following that that design or not, right? In the testing process. We want to see, okay, if we define the criteria of 5 nanosecond, we're going to measure it. But that time period is measured between which kind of like signal change. So, for example, like the most famous one is the time constants of a RC or RL circuit. Okay, that top, the time constant of that circuit. You simply say, okay, the time constant is like, for example, 1 second. Okay, but there is the specific definition is the rise time. The time constant is the rise time of a certain signal from 0% to the 63% of the final value. You see, we define the time, we define the signal that we want to measure, we define the low value and high value of change. Now we have a precise definition or writing for that rise time. Okay? Again, the term frame. Okay, but how if you don't look at this definition that we have, how we define frame? Normally, frame is a structure in your head. Okay, but when you look at the communication, it's completely different thing. It's not even compatible. It's not even like you can't even like compare these two definitions. The definition of the frame in communication, okay, is a sequence of bits composed of the data and control information that is transmitted as a unit. So now, when you wanted to use this terminology, after that word, after that term, you need to mention what sequence of bits, what type of data, okay, and what is from where to where is transmitted, okay, and what is the unit? How you define the unit of that packet data? It could be 8 bits, it could be 16 bits, right? So that's how it's important to pay attention to definitions of IEEE 100. So you have actually a professional writing describing your idea, your design, instead of vaguely just mentioning what you had in mind. Now, let's talk about those disasters that we mentioned earlier in our discussion. The first one, that Mars Climate Orbiter, the NASA project. Okay, what happened in that mission? Okay, that mission failed because the different teams in that project used different definition for impulse. You see how ridiculous is it? One word, impulse. They have different definition and different units for that, different teams in one project. So the navigation software defined that impulse as Newton seconds. The thruster control software team defined it as pound seconds, the imperial units. What happened? There is no cross verification. They didn't use the exact definition in the IEEE 100. Okay, and what happened is $320 million worth of equipment just lost forever. Just lost forever. Very simple mistakes. Definition of word impulse destroyed over $300 million project. Next example that we talk about, that Boeing 737 MAX. What happened in that incident? There is a parameter that they use in the design that called angle of attack as a parameter. So angle of attack is a parameter that they use in the design of that airplane. It's one of the engineering terminology. Now, the MCAS software, okay, used that terminology based on a single reading. But the sensor documentation was ambiguous, did not define what is the rate of data refreshment should be. Okay, it didn't define the tolerance of the error that we could have for that specific parameter. And it didn't define what is the test or evaluation should be conducted to make sure that this system is properly working. So what happened? Because of those vague definitions, we had 2 crashes for that airplane. 646 lives, human lives, is lost. One definition, one ambiguous definition of angle of attack. Now, who's responsible for that? The engineering team that made that mistake. It's not the pilot. It's not the airline. It's the engineering team that made that mistake. The third example that we had, medical device recalls. It happens through a vast period of time from 2012 to 2020. There were like blood glucose monitors. Okay, there were like cardiac implants. How critical that piece of equipment is. There were some infusion pumps that failed because of ambiguous statement and terminology. What was the ambiguous terminology? They said, like, for example, the statement says safe operating current. Simply that. What is safe operating current? Which current? How you define safe? How you measure if it's safe or not? How you control if it's not safe? Just mentioning safe, or they mention acceptable thermal rise. Thermal rise of which part of that piece of equipment? What is the acceptable temperature rise? What is the unit that you use? You know, these are the ambiguity for those terms which were not defined precisely based on the IEEE or IEC or even FDA terminology, okay, and made several casualties, basically, and they had to recall all their equipment. Simple mistake, simple terminology mistake. Now, we talk about the structure of IEEE 100. I'm going to review that. It's alphabetical organization. It has alphabetical organization. It's not just a word list. Every term has a meaning and has a specific characteristics defined in the definition. And it's domain classified. It's important to note that domain classified. For example, what are the categories? What are the domain in IEEE 100? The first one is electrical engineering. This is the general domain. The terminology in that category is used for all the subdomain of electrical engineering. Then we have several terminology that have different meaning in electronics, communication, control systems, software and embedded systems, power systems, in safety and compliance, and even in the environmental conditions. These are the categories that same word could mean different things. So you need to pay attention when and in which category you want to use that terminology, and is it classified in that? Is it categorized in that IEEE 100, that terminology? If it is, you need to pay attention to that. Now, let's talk about an example. In this example, we had a statement for sake of like your awareness. Any statement that I put in this discussion, all the examples, I didn't make those. I grabbed them from actual documents out there. Okay, so these mistakes already happened. Okay, one statement. the device will handle big voltages. How vague that is. I think you probably, based on our discussion so far, you can understand how problematic is that statement, and what's going to happen if we rely on that statement to design or validate a technology or a piece of equipment. Now, what are the problems? These statements are not precise. There is no measurable quantity, and it's not clear. They vaguely or like casually use the word big as an adjective of this noun, okay, which basically it doesn't have any numerical threshold. What is big? How you define big voltage? Is it over 600 volts? Is it over 600 kilovolt? Or is it over 1 volt? Okay? And we talk about that. Voltage is a potential difference between 2 points. Okay, that, for the sake of that statement, that big voltage, what voltage you mean? Between which 2 points you want to avoid big voltage? You want to handle big voltage. Between which point? Is it in input terminals, output terminals, across switches? Where in the system? And what is the condition? In what state that device has to handle that voltage? Do you mean it should handle that voltage in nominal or a steady state condition? Or it should handle during the transient condition? Or it should handle during a fault, when there's a fault occurring and we have overvoltage? In what condition we define that statement? Example number 2. The statement says, like, the device, a certain device should protect against a strong current. How vague that is, how problematic that could be. Now, what is a strong? How you define a strong? A strong is not a quantitative kind of like definition. We need to have a quantitative condition or a quantitative definition in our statement, so we could control it, we could measure it, we could define it, we could understand it. Everyone would not kind of like translate that strong to their understanding of the quantity that is there in their head. Because I could guarantee every one of you has different kind of like understanding of a strong current. What is a strong current? There are different values in your head. Now, it says protect against that current. How? How we want to protect? Is it going to be a fuse? Is it going to be a circuit breaker? Is there any relay in that device that should protect against that current? And again, following which standard we are defining that protection? Is it the safety standard for information technology equipment? Or is it the safety standard for medical devices? Or is it the safety standard for like power switchgear? What specific standard we are referencing to? And again, one thing that I didn't mention, that in what condition it should protect against a strong current: steady state, transient, or fault. Bad specification examples. In a signal transmission, I found a statement that says the system shall send signals quickly. Another example: it must handle big voltages without breaking. It should protect user from electrical shocks. It should resist temperature change and work under all environmental conditions. It must interfere with standard communication devices. Now, what is the ambiguity for that signal transmission? It says send signal quickly. What is quickly? What is the meaning of the quick? We need to quantify that speed. Okay, and what is signal? Which signal that device should transfer with that speed? Is it a control signal, or is something else? And when we say send, where are the two endpoints? From where to where it should send that specific signal with that specific speed? So now let's take a look at the enhanced version. Before I forgot. What is the type of that signal? Is it an analog signal or a digital signal? We have to define that. Now, let's read the enhanced version of that vague statement. It says the system shall transmit control signals with a rise time not exceeding 5 nanoseconds, okay, between logic levels, okay, measured between the transmitter output and the receiver input. You see how the difference between these two statements is? How precise is the enhanced version is regarding the first version, the ambiguous version. Next slide, voltage handling. We said the device has to handle big voltages. Okay, the magnitude is not defined. What is big? Okay, what is the condition? In what condition we have to handle that voltage? What is the measuring point? Between which 2 points we measure that voltage that we have to handle? Okay, so we need to identify the vague values, the vague characteristics, or the mischaracteristic that we have on that statement. So we didn't mention the voltage value, we didn't mention the measuring point, and we didn't mention in which operating condition we should handle the voltage. Now, let's look at the corrected version. The system shall withstand a steady state input voltage up to 600 volt of what kind of measurement? RMS. You need to mention that. The reader might think that you meant the peak voltage. Okay, so you have to mention the 600 volt, the unit, RMS between line and neutral conductors under nominal operating condition, referencing the origin of this definition as defined in IEEE 100. So if someone wanted to like read that sentence and it doesn't precisely know what is the normal operating condition is, go read IEEE 100 and you know what is the nominal operating condition is. Does that make sense? No. These are another 10 vague statements that I found in different writing in different documents. Most of them are official documents, okay, that regulators actually wrote. They exist out there. Now, let's look at it. Take a look, because we are gonna go one by one. I don't want to like read that in here. The first example, the statement is the device shall send signals quickly to the control system. What is the problem? Anyone can suggest? Go ahead. Yes. Okay, now let's enhance it. Very good, Echo. Let's enhance it. The enhancement is the device shall transmit. Okay, pay attention to that word shall. Okay, that's actually defines the criteria versus a suggestion. Okay, the device shall transmit what? Digital control signals. So we know that signals is digital, and we know it's a control signal. With a rise time, we wanted to see what's the quick. With a rise time not exceeding 5 nanosecond, that 5 nanosecond is defined between which two states? Between logic high and logic low, 0 and 1 is a digital signal. Okay, levels measured at the transmitter output and the receiver input. Now, according to the IEEE 100 definition of the signal and rise time. Do you see the difference? So now we precisely define, this is the difference between an actual engineer, okay, and someone that just heard about engineering. Next statement, next example. The statement is it must handle big voltages without breaking. Now, we already talked about this kind of stuff, so I'm going to proceed to the corrected, enhanced version of this statement. It says the system shall be capable of withstanding continuous input voltage up to 600 volt RMS, where between phase and neutral conductors, because voltage has 2 points, under nominal operating condition, okay, and another condition, and up to 1.2 kilovolt. Now here is peak, not RMS, during transient overvoltage. So now we specifically and with the detail define what we mean when we say the device should handle big voltages without breaking. Okay, and all these as defined in IEEE 100 voltage and root mean square. RMS should be, look into the IEEE definition so you know what RMS means based on the definition of the standard. Okay, it's not just vaguely using the function. You have to like read the standard definition. Now, next example. The statement is it should protect user from shocks if something goes wrong. Can you believe someone wrote that in an official document? If something goes wrong. Now, what should be actually the statement for this? It says, okay, first of all, protect user from what? All exposed conductive parts, pay attention, all exposed conductive parts shall be permanently connected to a protective earth conductor. This is how we define protection and how we define what is it, where we should protect, what is that we should apply the protection to mitigate the risk of electrical shock consistent with IEEE definition. So now you have to look at the definition of electrical shock in IEEE 100. Next example. Communication must be fast and use regular devices. Now, we have the standard, a specific standard for Ethernet communication, which is IEEE 802. Okay, the part 3 is Ethernet protocols. We are going to talk about that in next sessions, okay, specifically over that standard, but this is a standard specifically for Ethernet connection. Okay, now there is no referencing to that standard and compliances of that statement to that standard, because that's the precise standard for this specific device and technology. Now, what is the fast? What is the fast means? What is the minimum data rate that we have? What is the cabling requirement? On what type of connection we define this speed? Is it Cat5? Is it Cat4? Is it 5E? What is the cable that we define this speed for? Now, what is the enhanced one? The system shall implement Ethernet communication compliant with IEEE 802.3 transmitting frames. You know already, we talked about the frames, with a minimum data rate of 100 megabit per second. So now we define the speed and the unit of that. Okay, using category 5E or higher cabling. So you can't use cables or connection with a lower capacity of 5E. It's specifically defined now, consistent with IEEE 100 definition. Next example. The system shall ground itself properly to avoid problems. What is the enhanced version? All system chases and shielding elements shall be bonded to protective earth. Okay, so this is where in the system we connect to the ground. Okay, chases and shielding elements shall be connected to the protective earth. Which type of ground we are talking about? In accordance with IEEE 100 definition for ground, chases ground and protective conductor. Now, if you read the ground, the quantity that measures the strongness of, or like the how strong is the ground connection, is the resistance of the connection to the earth. So we have to have a quantity to measure if we are strong or not, or we are designing a proper ground connection or not. What is that? Grounding resistance between chassis and earth ground shall not exceed 1 ohm under normal condition. Now we have precise protection system okay, for properly ground the device. Make sense? Okay. Next one. It must detect if the power is not normal and shut down fast. Several problems with that statement. It's basically if every word is a problem. Okay, what is the enhanced version? The system shall detect what is the deviation. Under voltage and over voltage conditions, when the supply voltage deviates by more than plus and minus 10%, so now we have quantified a meaning for the deviation of nominal based on RMS measurement, okay, and shall initiate shutdown procedure within 10 milliseconds of what? Of detection. When it detects, 10 milliseconds later, it should be shut down. It should be a start procedure of shutdown, according to the IEEE 100 definitions. I don't have that. Sorry, it's not letting me read the. Okay. It should resist. It should uh come on. Let me see what is going on here. It should run well even when there is noise in the environment. You might think that, okay, this is actually more specific than others, but it's not. No. What is the problem? First of all, when we say noise in environment, we mean interference, electromagnetic interference. So we need to use the definitions for electromagnetic compatibility. What is noise? What is the problem? When we say noise, what is the quantity? How much tolerance we have against that noise? Because we can't have zero. And what is the standard compliance assessment? Now, the enhanced version is the system shall maintain functionality and communication integrity in environments with electromagnetic noise levels up to 10 volt per meter. Remember the unit. Volt per meter is the SI unit. Electromagnetic, radiated electromagnetic field. Confirming to the IEEE 100 definitions. Now, EMC has its own standard too. Okay, so if you are using a specific technology, you need to read that specific standard too. The display should show data clearly no matter what. What is the enhancement? The device graphical display shall maintain a minimum luminance of 400 CD per square meter under ambient lighting. Is not just always. Ambient light would interfere or like would change the measurement. Under ambient lighting, up to 10,000 lux, and in what viewing angle? Because it's different. It makes difference. In viewing angle of at least 80 degrees without significant loss of contrast, consistent with IEEE 100 definition of display and visual signal clarity. Next one, you might heard that a lot. Battery charging should be safe and fast. Now, when you say safe and fast, what that means? First of all, the battery charging module shall operate with a charge current not exceeding the manufacturer's rated limit of the battery pack. That means safe. Next part of the statement shall achieve full charge within 2 hours at the standard conditions, meaning 25 degrees of Celsius and nominal rated input voltage. So if there is a change on that, we don't have 2 hours. And now referencing, according to IEEE definitions for charge, current, and battery. Okay, we are at the end of our session. It's 11:35. Is there any question you guys have for this discussion? Go ahead.
And for like all.
Sorry?
Like when we go to write the report, it's like this slash all.
Yeah, every statement in your report, okay, should comply and be consistent with IEEE 100. Okay, write your report and try to criticize your own. Okay, statement by statement, sentence by sentence, identify the nouns and the adjectives, cross-check with IEEE 100, you would see how many characteristics and definitions you're missing in your original statement. Do you remember that a step-by-step process of implementing, applying IEEE 100 into your writing? We had identifying the noun adjective, cross-checking with IEEE 100, modifying, double-checking. So you can write your document or writing, okay, based on the casual, understanding. But after that, you need to sentence by sentence check with IEEE 100. The result of that process, now it's actually an engineering writing. Now it could be used outside of your own room. Did I answer your question? Any other question? We are going to have different assignment for each standard. Okay, for this standard, specific IEEE 100, I already posted the assignment. I think you would have access to that. And it's basically, I found 3 examples in actually, those examples are in federal documents. So I grabbed them in federal documents, okay? The statements that have problem, and I want you to fix them based on what we talk about. Okay, enhance the version, and when you enhance it, there is a several discussion that I asked for, like 2 or 3, understanding that you have from what mistake they made for the original statement, and what is the difference? What difference does it make when you modify that? Okay, so if you use the enhanced version, what it means when someone gonna use that statement or apply that statement to their design. Is that clear? Did I answer your question? Okay, any other questions from Zoom meeting? Any other questions? Okay, I also uploaded the lecture notes, the discussion, and the PowerPoint file into the chat of the Zoom meeting, so you can download that. And if there is no question, have a good rest of the day, and thank you for the attending this session.